All right, so today we have Riccardo Argurio tell us about SUSY breaking in branes at singularities, or more excitingly, the rise of the octagon. Take it away.
Thank you very much. So again, thank you very much for the invitation. It's a pleasure to talk at this meeting where the subject is precisely, and this time I really have a talk which is really on the main subject of the meeting, the series of meetings. Okay, so I will start immediately with the motivation. Oops. For some reason, just a second, because just a second, I need to do.
No worries.
Sorry, it's not reacting to the arrows. Okay, so I should have tried before, but
yeah, it's the thing we didn't check. Okay,
I just don't know how to go back. Okay, well, I will go only. I will try not to go back. Okay, sorry about this. It worked other times. Okay, so. Okay, so let me start immediately with the motivation. So the main issue of that I'm going to address in this talk is supersymmetry breaking instinctive. Okay, so the subject of supersymmetry breaking in string theory is as old as the string theory itself, and so I'm not going to review all the progress which has been done, but let me just say some triviality, good for the first slide. Why do we want to break supersymmetry? Well, okay, so obviously the obvious answer that we all know is that the string theories that we know best, and I would say also the only ones which are completely under control, are supersymmetric, while our low energy world, both particle physics or cosmology, is not obviously not supersymmetric. So supersymmetry has to be broken in between the scales at which we define string theory and the scales at which we. So this means that we want to have a supersymmetry breaking vacuum. Stable or metastable, we will discuss this in detail, in a theory which is supersymmetric. So this means what specifies to supersymmetry the well-known fact that this must be a case of spontaneous breaking. So in this case, it's a spontaneous breaking of supersymmetry. Okay, so now spontaneous breaking means that there is some scale below which, above which the theory looks supersymmetric and below which the theory looks non-supersymmetric. So obviously the nature or the way to address this kind of spontaneous breaking will depend very much on the scale itself at which this breaking happens. And so in particular, I will focus on the situation where the supersymmetry breaking scale is very low, or in other words, closer to the phenomenological scales and far from the string scale. Obviously, the other option, which is that the supersymmetry breaking scale is close to the string scale, brings in a different kind of techniques, and has been studied also over the years in many studies in particular. So we can consider like non-supersymmetric string theories can be also thought as string theories where supersymmetry is working at the string scale, and also what goes under the name of brane supersymmetry breaking is of this kind. Also. We have basically non-supersymmetric branes. Okay, sorry. Okay, so I would say that this is an important question, of course, and also revived in in view of these considerations about the swampland. So in other words, one might ask not only how to break supersymmetry spontaneously in a low energy in string theory, but even is it possible to break supersymmetry spontaneously at low energy string theory, or string theory as a UV complete quantum gravity theory? I mean, this is a question we can ask. And obviously, a negative answer would be very important and dramatic, in the sense that it would mean then that if SUSY breaking is impossible at low energies in string theory, it means that all SUSY breaking models that have been studied in phenomenology or else are in the swampland, and then it would mean that we would have to change radically the way we understand the top-down approach from string theory to phenomenology. Okay, but this is not what I'm going to do. It's not string phenomenology. What my point of view is in a setup where maybe I'm more familiar and also more appropriate to the theme of the meetings, which is the one of gauge gravity duality. So we're going to consider not a phenomenological setting, but string theory as a tool to learn about gauge theories. So the main, roughly speaking, the arena is to consider string theory with branes on non-compact singular spaces. And these are dual to quiver gauge theories, which means that, okay, so the question is which quiver gauge theories? This is a question that many people studied a lot, in particular Ami and everybody in this group and around him. So, okay, so why this is a setup which is exactly what I'm aiming for is obviously these configurations. We start with BPSD branes on Calabi-Yau singularities. So this is a setup which is perfectly supersymmetric. Calabi-Yau singularities preserve supersymmetries, BPSD branes preserve a compatible amount of supersymmetry. And so supersymmetry is preserved, let's say, at the string scale. This is built in this approach. But then one has to understand what happens to the dynamics of these branes when we go at low energies, or in other words, in the deep bulk. And so the basic assumption of this point of view is that a string theory configuration has a supersymmetry breaking vacuum if and only if the dual quiver gauge theory has a supersymmetry breaking vacuum. So, okay, so this will be taken as if and only if relation. And then obviously the stability of this vacuum will be crucial. And again, there is a direct relation between the two sides of the duality. So we will be interested in supersymmetry breaking vacuum which are completely stable, or metastable but with a parametrically longer lifetime. Okay, so this, as I said, also in this context is is a story that goes back to almost 2 decades, actually more than 2 decades. So for one possibility which has been discussed at length is the one of putting anti-D3 branes on a deformed conifold. So the deformed conifold is the geometry that one gets in the Klebanov-Strassler setup. So putting fractional branes on the conifold, then this triggers a deformation of the conifold, which is a supersymmetric deformation. But then in a paper in 2001, Katcho, Pearson, and Verlinde proposed to add a certain number of anti-D3 branes. So which have, in other words, which have a supersymmetry which is the opposite of the background, so it breaks a supersymmetry. But then they are drawn to the tip of the geometry, and they break supersymmetry in a way which is spontaneous. And they also show that this is metastable because this Cleveren-Strassler geometry, gauge theory has a very rich moduli space with many branches. And in particular, they showed that the anti-branes, the SUSY breaking state with the anti-branes can tunnel to a mesonic branch, which is supersymmetric. So this is metastable, but with a lifetime can be tuned to be very large. And this is, funnily enough, a similar situation in pure gauge theory was engineered only 5 years later in the famous model of intelligator Seiberg and Shi, where we also have the same situation. We have a metastable vacuum, let's say, at the origin of the moduli space, of the would-be moduli space, field space, and supersymmetry breaking, supersymmetry preserving vacuum further away. We investigated back then actually the link between these two situations, and well, we found a link, even though it's difficult to engineer in generality ISS in this setup. Oops. Okay, so but then what other models are there models of stable dynamical SUSY breaking around? So in field theory, these are well known. So these are known since the 80s in the work of Affleck, and Seiberg. Basically, they found most of them. And so let me just exemplify two of them, which are going to be relevant for the rest of the talk. So the simplest one is the one called SU5 uncalculable. So you take an SU5 gauge group with matter which looks like one family of unified theories, so an antisymmetric and an antifundamental. With such a matter content, the superpotential cannot be written. But then there are some clever arguments that one can make about the global symmetries and the absence of moduli space that tell us that the supersymmetry must be broken. And then the only scale of this model is the one of the dynamical scale of the gauge theory. And so we expect the SUSY breaking scale to be given by a scale of that order. So the energy, which is in some sense the order parameter of SUSY breaking, is going to be the dynamical scale to the fourth power. But there is nothing to compute. It's an argument which tells us that supersymmetry must be broken. In other situations, one might have more control, like in this 3-2 model, which is also called the calculable model. So again, here we have a structure which looks like one family of the standard model. So we have an SU3 and an SU2 gauge group. Actually, this model can be written as a quiver. So we have like a quark doublet, U and D quarks, and a lepton, and a superpotential, which looks like the superpotential of the MSSM. But note that only D appears in the superpotential and not U. Here, one can show that at the effective level, so there is one can generate an Affleck-Seiberg superpotential. And eventually, the model breaks supersymmetry in a way which is reminiscent of a generalization of monograph-Ferti model. So basically, one cannot solve the F-term equations. In this case, for instance, for small coupling in the superpotential, the energy of SUSY breaking can be tuned to be smaller than the scale of, in this case, the SU3 gauge. And also African and Seiberg in the 80s also provided generalizations of both of these models. Some generalizations. So now the question is, can one engineer a brane configuration which reproduces one of these models? And note that these models have both features which are not quiver-like, in the sense that, for instance, in the SU5 model, we have an antisymmetric, and in the usual quivers, we have only bifundamentals or adjoints. In the SU3 and SU2 model, we have a superpotential which distinguishes between two fields which are otherwise have the same gauge charges. And this is again something which usually doesn't happen in quiver gauge fields, engineered by branes at singularities. So how do we go around this problem? Well, this was already discussed 15 years ago, let's say by others, where the idea is to add orientifolds. So that paper was did in a systematic way. One adds orientifolds, and then it is possible, it was shown already in that paper, that it was possible to engineer the SU5, the uncalculable model. At least the two geometries were shown where this SU5 model could arise. The idea is that orientifolds allow not only for SO and USP groups, but also of matter in two index tensor representations, so symmetric and antisymmetric. And this okay, solves the problem of the presence of the antisymmetric in the SU5 model, but also allows, by the fact that the antisymmetric in SU3 is the same as the antifundamental, it can tell us that maybe there can be a distinction, a natural distinction between the U and the fields of the SU3 of the 3-2 model. So in these cases, the QFT analysis tells us that the SUSY breaking states are stable. So, okay, so the most, so why is this interesting in general, not only for gauge gravity correspondence? The idea is that, for instance, this KPV setup with the anti-branes has been used extensively for the KKLT construction, and so eventually to get the Sitter vacua in compactifications of string theory. But the fact that KPV is metastable and that people have argued about the actual metastability or not of this KPV state has been debated for a long time, and in particular, I think sometimes even heatedly. And actually, I'm not sure now 100% of if there is a consensus or not. I'm not sure that there is a consensus. But in any case, so we in all the critiques of KKLT have been mostly focused on this metastability of the anti-detail branes. So then we thought that indeed instead of starting with a metastable state, but starting with something which is fully stable, could be a very nice alternative for constructions like KKLT. So we focus on this. Our focus of the recent work is on this stable SUSY breaking. So this is work so done in collaboration with Matteo, Seba, Eduardo, Shani, Antoine, and Baldo over the years. So started a smaller group, but then all the last papers are in this group, which we enjoyed a lot the collaboration, so we continued in a live collaboration. So, okay, so what is actually the starting point of this effort was actually a plot twist, which uncovered the fact that what we thought was stable actually was not stable. So this is a work of 2018 of Pedro Angel and Ginevra Buratti, which took a closer look at one of these realizations of SU5, in particular the C3 over Z6 singularity. Then they discussed, so the idea is that you get, if you just put like a minimal amount of fractional branes, you have the SU5 model. But then the idea was to see what happens if at the singularity one adds also a number of regular D3 branes. So basically this means adding n to the rank of all the gauge groups of the full quiver. And this is also a necessary step if one wants to have really a decoupling limit and let's say to see these models arise in a gauge gravity duality perspective. And what they found is that if one adds n regular D3 branes, actually this model ends up having an instability. The reason is that the singularity also has fractional branes called n equal 2. These are fractional branes which also, let's say, behave as if the singularity is non-isolated. And so this extra direction over which the singularity is not non-isolated is like a Coulomb branch in the gauge theory, an n equal 2 Coulomb branch. And actually what they showed is that there is a SUSY vacuum along this Coulomb branch. So basically the regular brane split in n equal 2 and some n equal 2 go to the singularity and spoiling the SUSY breaking nature of the vacuum. So now, okay, I have also a slide on what is an n equal 2 brane. I'm sure that most people here know what it is, but let me say it. So these are toric diagrams for representing the singularities. So the basic, let's say that the most basic ones are the conifold and C2 over Z2. And the main difference between these two toric diagrams is that the C2 over Z2, so this is actually an n equal 2 singularity. And the fact that there is this node along an edge tells us that there is an n equal 2 fractional brane. So this is an n equal 2 singularity. So one is granted to have n equal 2 fractional branes. And so the fractional branes of n equal 2 singularities are n equal 2 fractional branes. And their distinctive feature is that there are points here on an edge. While, for instance, in the conifold, there is no edge with a point, and so the conifold does not have any n equal 2 fractional brane. But as you see, other singularities, like the two singularities that have been considered in the paper of 2007, were C3 over Z6 and PDP4. So these are the toric diagrams, and you see that both of them have edges with points on them. So here we have a lot of them. And also the PDP4 has 2 edges with a point. And so both of these singularities have n equal 2 fractional branes. And so the question is, well, is this problem found in C3 over Z6? Is it also fits the other example or other examples that one could find? So this is what we did in the first paper, so with Matteo, Shani, and Antoine. And so we scanned, and so basically what we did was to take, let's say, the manageable amount of toric singularities with, let's say, a maximum of of nodes, limited by how we could draw them on a piece of paper. And we looked for singularities where we might find the SU5 model, or also, why not, the 3-2 model. And so what we did was to perform this scan and find actually that in many of these singularities you could find, so in many of them, so this is 2 tables, so these are like pseudo-del Pezzo-like singularities, and these are orbifolds. These are basically generalization of the PDP4. This is generalization of the C3 over Z6. And so you see that the SU5 model has been found in all this, is typically found in all of these singularities. Of course, I didn't list the ones where we didn't find. We could see that there was no way of finding an SU5 model. And the 3-2 model could be found also in some singularities, but let's say it is less frequent. So the 3-2 model here realized that I didn't list, but it's also found in the PDP4 and in the C3 over Z6. We can find the niche occurrence of the 3-2 model.
Sorry. These are tilings where there is a single gauge group for the SU5 and just 2 gauge group for the 3-2, or you have a collection of U1s as well, right?
Yes, yes. So I will show an example in a second, but yes, in general, so you see all the in the model, so the antisymmetric. Well, I'm going to show it in a second, but you will need some flavor gauge groups, right? So the flavor gauge groups will be SU1 or SO1.
Mm-hmm.
So
Okay.
those I don't list. So I will show it in some examples. So to recover all these models, more than 1 or 2 gauge group faces of the dimer will be turned on, but of course, in all these models, only a subset of the faces of the model of the dimer will be turned on. I don't know if there was another question.
Yeah, I just wanted to ask a maybe more basic question, but when you say that you find the SU5 or the 3-2 models in those geometries, you mean that you find a certain brane configuration that you can put on these singularities?
Yes,
so that, and then this SU5 or this 3-2 will be I guess his Ami's question, will be a subset of it will be a sector of the theory.
Exactly.
So, okay.
Of course, let's say that first we work out the non-anomalous configuration for the whole dimer, and then we check if there is a way to specify the nodes, the ranks of all the faces in such a way that we have the SU5 or the 3-2 model.
Mm-hmm. Okay. Yes.
So I'm saying that the anomaly cancellation conditions are done on the whole dimer before specifying the specific ranks. Otherwise, you would also always have like a single SUN in any quiver.
Hmm. Yes. Okay.
Okay. Very good. So this was a scan that we did, and we stopped after Z30, as you can see, and also PDP5 didn't get higher than that, but so we had like 20 or so models, including 3-2. And then we checked if there was an n equal to instability, an instability like in C3 over Z6, and the answer is yes. So we can see, first of all, that all these models contain n equal to branes. So if you go and look at the toric diagrams, all these models, they contain n equal to branes. And then one can also show in all these cases let's say the n equal to brane, the existence of this Coulomb branch leads to an instability. Actually, this is, we didn't do the computation for all these examples because we could show actually no generality. that if there is an SU2, SU5 or 3-2 model, and there is an n=2 brane in the dimer, then there will be necessarily this instability. So this is a basic consequence of having non-trivial anomalous dimensions. So then we can ask a question, okay? Okay, so we saw here, we have like 20 models, and in all these models where we could find SU5 or 3-2 model, then there would be n=2 branes. So what I didn't show on the table is that there are a lot of singularities in the same. So in the batch of singularity that we looked at, there were many which didn't have n=2 branes, but in those ones we could show that it was impossible to find an SU5 or 3-2. So then the question is it possible that can we show that the n=2 brane, the presence of an n=2 brane is a necessary ingredient to find an SU5 or a 3-2 model? Then that would mean closing the loop, that then the n=2 brane produces the DSP model, but then also makes it unstable. That would actually show that stable SUSY breaking is impossible. Okay. And so based on the evidence we had so far, we set out 2 years ago to try to prove this. And obviously, the idea was to use, let's say, extensively dimer techniques to see if this was the case. No. Okay. So, okay, again, dimer techniques, feel a bit embarrassed to present it here, but let me just show a slide about what I mean by dimer models, and also let me use this opportunity to also highlight what is important for me, which is the oriented-fold action. Okay, so these are two examples of dimers. So here you have the typical orbifold. So this is the C3 over Z6, and this is the PDP4 actually. So the first two examples where we had the SU5 model in the paper of 2007. So you see that in this case it's an hexagonal lattice because it's an orbifold. This is more general because it's
Riccardo?
yes.
Yeah, so there are two possible Z6 actions, right? There is one which preserves n=2 and one which...
So this is, sorry, it's the n=1 Z6.
Yes, okay, thank you, yeah.
Yeah, so, okay. And so, so one on the dimers, one can read many things, but I don't need actually to explain this here. Also, I don't need it. Let's say, I mean, all the details are in the papers. Will not bore you down with details about that. But the important thing is that the dimer, so let's say the quiver gauge theory is defined by this unit cell of the dimer. So you see that there are repetitions. So all the nodes 0 here, the faces labeled by 0 is the same face. So this is a unit cell, and the same here. Well, here it's centered on phase 5. And so orientifolds, as was proposed in the seminal paper of 2007, are Z2 involutions of this unit cell. And so the Z2 involutions that were proposed at that time are basically of three kinds. So one is a point involution, but one can see that actually because of the involution the points are 4. I mean, because of the periodicity also there are 4 fixed points. Then there can be, and this is true for any shape of the fundamental cell. of the unit cell, I mean for any tilt. But of course, the dimer itself has to support an involution. So as in this case.
So Riccardo,
Yeah.
do you also entertain involutions of order 3 and 6 that you could have?
No. We considered only involutions of order 2. It's an interesting question. I was just about to say that there were the young people in the collaboration came up with a new involution, which is this glide orientifold. So this is something new with respect to this, but now you're suggesting something more. But no, this I really consider.
Yes, there was quite a bit of literature on these objects which are called S-folds.
These are the S-folds, yes.
Yeah.
No, so we.
So you focus on those perturbative objects, but there could be some.
Yeah, sure. I agree with that, and I think okay. So no, we don't consider the S-folds. That's true. Yeah, but it's an interesting perspective in the sense that this could enlarge the number of models, of course. Yeah. But so actually in the papers where we discussed this, we only looked at this, let's say, traditional C2 involutions. And so there is also the line orientifold here when the unit cell is like a rectangle, and then there is this diagonal fixed line when the unit cell is a rhombus. Okay, so let me do a sample computation for you of how we go about to try to show that the presence of a DSB model leads to, has as a necessary condition n equal to brane. So in order to engineer an SU5 model, then imagine that we found that, so this is like just a piece of the dimer. But then we see that in order to have, let's say that this is going to be the SU5 gauge group, and this is going to be an SO1. Okay, so this is by anomaly, let's say by anomaly consideration condition of the whole dimer, one finds that this is a possible situation. Then if we want to have an antisymmetric of SU5, then it means that there has to be a fixed point on the edge between the SU5 and its image. Then if this phase has to be an SO1, then there has to be a fixed point, a different fixed point, obviously, right in the middle of this phase. But then if I see the image of these two faces, then I have 1 prime, 2 prime, so no, sorry, 2, the same. It's not 2 prime. And then this is basically the bottom of the unit cell. But then you see that I have a stripe here. This defines, so I have this light blue stripe, is what in dimer parlance defines an n equal 2 fractional brane. So in this case, so this, if you know what I mean, you know how it works. If you don't know, just believe me, but a stripe in the dimers is something I can cross with having all white nodes on the left and black nodes on the right, is what defines an n equal 2 fractional brane. It's a loop in the dimer that I can go around. So this is an n equal 2 fractional brane. And so in this case, I see that the presence of the SU5 model implies the presence of an n equal 2 fractional brane. And then eventually, when I work out the dynamics, the n equal 2 fractional brane will tell me that the SU5 model is actually not stable when I add n radial branes. Okay, so then we do this for all the possible realization of SU5 and 3.2. So it's quite easy because there is a finite amount of ways in which we can try to embed, you know, like the SU5 has to be next to some fixed point or fixed line to have the antisymmetry. Then how you're going to have the anti-fundamental, then you need an SO1 or an SU1 and so on. So the 3.2 model is very similar. And we find something as in the previous slide for like for all the realization of the 3.2 model, and also for all the realization of the SU5 model, except one. Okay, so we found an instance where we cannot derive from the, let's say, the local realization of the SU5 model, the existence of an equal to fractional. And this is in the case where we have a fixed line. And then basically we have an SU5. So, oh, sorry. Okay. Sorry, just a second. To do this. When you, so this is an SU5 phase. 3 is also an SU5 phase. 2 is a SU1. So you see that this is a sort of twin SU5. So you have two SU5 models which have in common the same flavor group. Okay, so okay, and in this case you see that it closes on itself. So basically the only consequence is that there has to be this hexagonal cluster in the diamond, but it is local, so there is no it doesn't imply a periodicity of the, let's say, it doesn't specify a characteristic of the whole fundamental set. So the question is, okay, good. So there is more work to do. Is it possible to have such an hexagonal cluster in a dimer in general? Okay, so either you prove that this is impossible or you find an example. And then there are ways, smart ways, especially for our younger collaborators, to find a dimer with the required, with the presence of such a required sub-dimer, let's say. And this is a solution, actually the simplest that we could find. Okay, so the requirement was to find the hexagonal cluster and in a singularity which cannot support n equal to fractional branes. Because remember that if there are n equal to fractional branes, then there will necessarily be an instability. So the requirement was to find the hexagonal cluster in a singularity which has no n equal to fractional branes, and this is the simple. So you recognize here the hexagonal cluster, and then the rest of the faces make up for the singularity, which has this toric diagram, which looks like an octagon, and so we called it the octagon. And so this is how the octagon arises. And so here in this picture, I already showed, so it has to have, so you see that it has to have a line oriented. Okay, so this was also a guiding principle to find the toric diagrams, because actually toric diagrams which have line oriented forms are also classified. This was actually also one of our one of the papers in the list, and so this is it's a line oriented of this kind with two lines, and one is gives rise to USP groups and antisymmetrics, and the other one gives rise to an SO group. So this is phase 7 and symmetrics. And then it turns out that we will turn on these phases, and also we needed to turn on phase 7, but which is completely disconnected, and all the other phases are set to 0. So 4, 8, 11, I mean 4, 8, 5, 6, and the images are set to 0.
Riccardo?
Yes.
What are the conditions which are set in order to find this solution? Or this is maybe one choice. Is there a systematic search?
So I think this was the best bet. So we actually came up with the toric diagram as probably the simplest singularity that finds this hexagonal cluster. And then we found the non-trivial thing was to show that there was indeed a way to write a dimer that has this symmetry.
Mm-hmm.
Now we tried like the next to simplest, something like with two nodes here.
Mm-hmm.
And the edges, so still without n equal 2 branes. And in that, so in the next to simplest toric diagram, we actually didn't find a realization of this hexagonal cluster. So it's not obvious. Maybe we were a bit lucky. But we don't. We assume that there must be other more complicated singularity that also happen. But this is certainly the simplest.
So you're saying that there could be some systematic search which goes over all toric singularities with 1 point, 2 points, and so on, and systematically looking for all possible tilings and searching for this particular hexagonal.
Yes, yes, but I think it would be not straightforward because you have to. I mean, you have to go to the definition of the dimer, and so it's not. It is not straightforward as a search because let's say that in a generic. I mean, there are Seba is an expert, of course. There are ways to generate automatically a dimer from a toric diagram. But this will typically not give you something which looks like there is an orientifold and also which doesn't look like you will find what you need. But we refined a bit. I mean, I think actually Valdo has a paper on his own. I think it's a proceedings about that. So if you're interested, I can refer you to that. So in other words, the idea is to find a dimer, but putting as a constraint the fact that it has this line orientifold. You know that it has to have it because the toric diagram has the symmetry. So then you can impose the symmetry also on the dimer, but so it makes it more complicated to find the.
But do you actually need the line orientifold?
Yes, yes, this is absolutely at least.
Mm-hmm.
For us, yes, it was crucial because we wanted to find this.
I see. Okay. Mm-hmm. Yeah. And did you run over all possible toric phases of the given model?
Of this model, we contemplated a bunch of them because at the beginning we thought it would work with a diagonal line, and it didn't. So yeah. Not systematically, but yes. So, and there are many toric phases where this is not happened.
I see. So you said that there's room for making a systematic search.
I guess.
Yeah.
But I don't expect it to be. I mean, I expect the tools needed to be adapted. Okay.
Mm-hmm.
Okay, so maybe let me. So this actually it's notoriously difficult to consider duality cascades when there are antisymmetrics and symmetrics, but here, so we cannot do it in full detail, but the numbers are such that it's very likely that there is a cascading G flow. There is certainly without the orientifolds. After the orientifold, one needs maybe some generalization of cyber dualities, but there seemingly is an cascade, an RG flow like with cyber dualities. Okay, so then assuming that there is this RG flow, at the bottom we will have this cluster, this hexagonal cluster, As I said, there is also a decoupled node, which is a pure superunionist node. So I'm not going to discuss about it. But then the theory which remains is this one. So there are 3 gauge groups. So the middle node is a sort of gauging of a diagonal of the flavor gauge groups of the 2 external nodes. And then there is also, interestingly, a superpotential, which is a sextic superpotential, which is obviously there because of the hexagonal cluster, which means that there is a sextic superpotential. Now, if we set m equal 1, then we are we have 2 SU5 models. And by the group theory here, one can see that the superpotential is actually 0. So we have 2 decoupled SU5 models, and so supersymmetry is broken, and it's even broken twice. By construction, one of the requirements to find the singularity was that there were no n equal 2 branes, so there is no instability with 2 n equal 2 branes. And then also all the other instabilities that could arise are also not there. So that this is common, this is nothing new. This is basically instabilities that are not there also in the other models. Okay, so n equal 4 Coulomb branes, you could say, are the regular branes stable or not? Yes, they are stable. String instantons do not arise, basically for the same reason that W is equal to 0. And also, one could worry about partial resolutions, but also those are abstracted. So then I would say that the answer to the question, is it possible to have SUSY breaking, stable, spontaneous SUSY breaking in this setup? So then, and then this setup is instinct theory, so instinct theory. Then the answer is yes. And I would like to underscore that there is really an interplay between all the ingredients are needed. So we need the geometry, we need the fractional brane probing it, so this n equal 1, and the orientable. All of these ingredients are necessary. Okay, so the orientable, as we said, and the geometry has to be very specific, and then we have to put some fractional branes. So the question is, obviously, what is the picture from string theory? No? Because the argument in favor of SUSY breaking is a gauge theory. This is the argument of 84 of Affleck, and Sander. So how do we see SUSY breaking from string theory? And here we could also object, first of all, that, okay, here basically we're adding 1 fractional brane, so how can we have geometric intuition with 1 fractional brane? Because it's going to be maybe a stringy mechanism, not a geometric mechanism like the deformation of the conifold in the case of Cleveland. So then, well, can we generalize? So I showed that there was SUSY breaking for m equal 1, but what about general m? Can we generalize? Can we find something where we can take the number of fractional branes to be large, no? So that then we can maybe aim at a better control. So this is the object of our most recent paper.
Yeah, Riccardo?
Yeah.
Regarding the scales of supersymmetry breaking, I mean, before you generalize, do you have one scale from the field theory, or do you also have an additional scale which comes from bending of the branes?
No, so from field theory, the only scale, so this is we find the SU5 model, which has a single scale. So the scale is basically like the dynamical scale of the gauge groups at the bottom of the cascade. So it's really like saying, we have SUSY breaking, which is in principle of the order of whatever controls the dynamical scale at the bottom of the cascade. Now, as you know, in like in Cleveland-Strassler, let's say that scale depends also on m in some sense, on the number of fractional branes. here m is equal to 1. So, but if there is a cascade, which brings us back to this SU5, a long cascade, let's say, then we assume that the scale which controls SUSY breaking is small with respect to the string scale. It is a gauge theory scale.
And you have just two scales?
Well, in this case, we have, well, okay, no, we assume the scale of the two groups to be of the same order. Yeah, we assume that. I don't think anything interesting comes out of taking a hierarchy between the two scales.
Okay, I see.
So then this is the object of our latest work, was the generalization for M large. So now we indeed have three gauge groups and this superpotential of order 6. So this is not one of the generalization proposed by African insider. So the generalization of the SU5 was some SUM with antisymmetric and a bunch of antifundamentals, but they had a cubic superpotential and only one gauge group. Here we have three. But then we can analyze this model, nevertheless, and along the lines of African cyber. And what we find is an interesting result. So we find that if M, any M, but if it is odd, then the theory has a stable SUSY breaking vacuum. If M is even, on the other hand, then the vacuum is run away. So it is SUSY breaking, but we run away to infinity in some direction in field space. So this is very puzzling, and from the point of view of string theory, so this was already true for the single the generalization of the single SU5. But from a perspective of string theory, then it's reminiscent of something like discrete torsion, or something that distinguishes between even and odd number of fractional branes. And indeed, let me stress that let's say the number of one of the nodes of the dimer is a USP node. And in the way we count, the USP node has to have even has to be USP n with n even. Okay, then this node is set to 0 in a configuration that we consider. But the idea is that if one adds a regular brane, then this means that we are adding, let's say, 2 units of rank to all the nodes. Okay, so when I say rank, I mean the SUN. Okay, the n of SUN or n of USP. Okay, so this is one thing. But so the fact that the USP node has to be even doesn't mean that the other nodes, so there can be fractional branes in the other nodes which are not equal. So in more detail, what happens is that for M odd, one basically sees that this model is reduced, let's say, on the moduli space to precisely this twin SU5, but with a USP M-1, which now is even. But for M even, one has a reduction to SU4, twin SU4. So this is not pure gauge SU4, it's SU4 with an antisymmetric, so it is run away. And the USP N, which is actually super immense. So, and the runaway in this case, if one looks in more detail, the runaway is in the direction of some Pfaffian operator. So it's the Pfaffian of the antisymmetric of SU4, which can be traced back to the Pfaffian of the antisymmetric of these two gauge groups. Now, the Pfaffian can be written only if M is even. So if M is odd, I cannot write the Pfaffian, and geometrically this tells me that the moduli space doesn't have the directions along which to run away, and that's why we have stable SUSY breaking. So on the geometric side, it looks like the Pfaffian morally is is what remains of a d-baryon after the orientifold. And so, since we can somehow relate d-baryons to partial resolutions, so it's deleting one line in the one edge in the dimer, so then it looks like the odd fractional brane actually seems to be inhibiting this partial resolution in the geometry. Okay, sorry, I'm going over time, so let me maybe quickly go over the geometrical picture that we think we conjecture to be what is happening. So the octagon has a complex deformation. No? So what I didn't stress maybe is that the fractional brane which leads to this hexagon is a deformation fractional brane. So there is a complex deformation associated to it. Now the orientifold turns on some of the phases corresponding to this deformation fractional brane, but not all of them. So in some sense, the orientifold is misaligned with the 3 cycle of this deformation. And so this leads to SUSY breaking. And if there are these fraction directions, run away from this direction. This is the typical behavior of what were called 15 years ago SUSY breaking fractional branes, which are usually run away, like in Del Pezzo 1 and so on. But then comes in this odd fractional brane, which somehow implements a Z2 valued abstraction, which kills this directions along which the runaway is taking place, and so stabilizes let's say the runaway at a finite distance, and so makes the supersymmetry breaking stable. Okay, so let me just say that finding a gravity dual, now said all of this, is obviously not easy, but maybe not impossible. Also, let me underscore that this stabilization is due to one fractional brane, so it's possible or even likely that even if the gravity dual exists, maybe it's not completely smooth, because there will still be a localized fractional brane. So let me end now. Okay, so here just stating that we think that in this non-compact setup, we have found a fully stable SUSY breaking vacuum string theory that could have a geometric picture for, we tried to argue what the geometric picture for SUSY breaking would be in string theory, not only in H theory. Then we can also argue what happens if we are not in a non-compact setup, but in a compact setup. So more in a perspective for the Swampland or for compactifications or for phenomenologies. So this is what we are proposing again. And so there is a SUSY breaking at the tip of a cone, which is asymptotic radius 5 up to log corrections, like relevance translate. So if you read carefully the non-supersymmetric radius conjecture of Argurio and Baffa, this is quite crucial that it is really asymptotic radius, so that there is a conformal filter at the boundary. That's the argument. And so, so it's not in contradiction. But obviously, we can use this stable SUSY breaking setup in a compact Calabi-Yau. So imagine that we can embed the octagon in a compact Calabi-Yau, and then we imagine that there is a long throat with the octagon at the bottom. And then that would be exactly the same spirit as how KPV or empty branes are used in peculiarities. And so in that sense, the story will be completely similar. So we could use this to uplift the peculiarity scenario to a simple vacuum with small cosmological constant. So this was already proposed by Tolazza and Angel a few years ago, using this C3 over Z6 singularity, which was then shown not to be actually suitable. But so the added value of doing this would be to avoid all this debate about metastability of KPV. So if that decay channel was used as a proof that KKLT is in the Swampland, then using the Octagon instead of KPV would disprove the Swampland in that sense. But well, okay, I mean that's it's left for people who are more expert on these issues than us. Okay, so I'm finished. Sorry for 5 minutes over time, and I leave this. I'm done.
Okay, it's very good. So then let's thank Riccardo.
Thank you.
Questions?
You look at this brain system as a set of brain webs. Was there any attempt to find the minimal configuration?
Sorry,
So
you mean the PQ web?
so you have 5 brains which are
Yes, yes.
bounded by NS brains, so they form bound states. So
Yeah. So okay, so we can go to take the octagon toric diagram and build the toric web, no, associated to that.
Yeah, so the toric web is one thing, but here I'm talking about the brain tiling. So the brain tiling is made of D5 brains, which are bounded by Neveu-Schwarz 5 brains, and so they naturally form two independent sets of brain webs with different orientations. So now you have a minimum problem to do, to find the brain system which is stable under those initial conditions. So
okay, let me say other way that we didn't think about the problem in this sense, but do you think that if you know that the minimum configuration is a SUSY breaking, do you think that the tools that are available would allow for finding a non-supersymmetric minimum?
I'm hoping that this is the case. The problem would be to write down a set of equations, some kind of non-jumper, and such that their solution gives you the minimum, the non-supersymmetric minimum. You lose holomorphic dependence, but somehow you end up in a stable brain system. And
yeah, we haven't looked at that, but
right. So the thing is that you have the 5 brains push; they want to go out. NS brains are bounding on both sides, so they are also subject to forces. So there is a system of forces in the brain.
But in that, for instance, would you expect to see this alternating behavior between even and odd M?
That's an interesting question. I don't know. I mean, I don't see how it would come about.
Yeah, I mean, the problem is that there are, I repeat, there are three ingredients which are important. So the octagon, so the geometry, the very specific geometry, the orientifold, and let's say the odd number of functional. So this is
I see.
the three things which. So in other words, what I'm saying is that you need something which can, like apprehend all these three ingredients.
Yeah.
To hope that you will find the non-supersymmetric minimum. That's why, in some sense, the geometric dual, the gravity dual will be probably harder to find.
Mm-hmm.
But okay.
I see. Mm-hmm.
But
Okay.
I mean, we will look into this thing.
Yeah, Antoine is here. I see that.
Yes, I was disconnected. I wanted to ask a question that maybe you asked already, but about your third ingredient.
Yes.
So the branes. So because I would like to understand what depends on the geometry and what depends on the brane content. So you picked a one parameter family, right, with this parameterized by M.
Mm-hmm.
Is this a choice, or is there any other choice of number of branes which would satisfy having no anomalies and everything? And did you choose arbitrarily this one dimensional, one parameter family, or is it the only one?
So historically, what we did was to look for the SU5 model. Okay.
Okay.
So then it was obvious that we wanted to have this cluster with 5, 1, 5. Then we asked ourselves, okay, instead of 5, 1, 5, we have n plus 4 and n plus 4. What happens? But there are many, there are more fractional branes in the octagon and more, still a number of fractional branes in the orientifold of the octagon. And I'm not sure that we scanned all possibilities. Because the fact is that, okay, so let me say it again. So at the beginning, we looked for the models that we knew were stable. So the SU5 and the 3-2. And then because there was some reason that like the generalization of the SU5 and the 3-2 could not be found. It's a very simple argument about, the gauging of the flavor groups spoils the SUSY breaking, the stability of the SUSY breaking vacuum. So it's only afterwards that we found out, we studied this model with M, and we found that it had a SUSY breaking vacuum. So in other words, what we are looking is for models that we know that break supersymmetry. But we could have, it's more difficult to say, let's consider a generic situation and then let's see if it breaks supersymmetry. This we didn't do. So what I cannot exclude is that there are other configuration of fractional branes that provide the SUSY breaking in some models which are not known to break supersymmetry, but that are still out there to check. But that's basically the answer. Okay. But if you are asking about, instead of having like the same gauge groups but with different ranks, then this does not work. So this is really the only parameter we have for that set of gauge groups.
Okay.
Cyril, you raised your hand.
I did, like a good student. Riccardo, thanks for the nice talk. My question is about can you say more about the fit when you have D3 branes, like for regular D3 branes, and how the cascade looks like?
So you're asking about the cascade?
Yeah.
So the cascade, the answer is that we don't really know, but we have some partial insight. So if you take the octagon without the orientifold, then the fractional brane that we put is definitely leads to a regular cascade. This is very painful to do, but straightforward. So this is one thing. Then you could say, okay, with the orientifold, basically you take the cascade without the orientifold, and then you sort of orientifold the cascade, and then you say that it's going to happen like this. So,
Right. So you're saying even if I don't have the orientifold, then I would have the deformation brane that breaks SUSY?
No. Sorry. No. Without the orientifold, you don't break SUSY.
You don't break. There is no like runaway type SUSY.
No. So it's
okay. In that case,
it's like a Klebanov-Strasser, like
okay,
more
sure.
complicated.
Yeah.
Then you could say, okay, I just orientifold it, and I assume that everything goes fine. But so this is something that with Matteo we looked at some years ago before these papers, and actually it cannot be granted. Sometimes the cascades in presence of orientifolds are more complicated because in very simple orientifolded quivers, but like ones where you have only USP nodes or only SO nodes, then you will see that the periodicity of the cascade changes. So you will hit a wall. Another problem is that you don't really know how to do dualities with antisymmetrics and symmetrics, even walls. So it's not obvious how to do cascade with that. But the best way to, but let me say that in the octagon with the orientifolds, there is the same number of, so there is one USP and one SO node, the two symmetrics and two antisymmetrics. So we expect eventually the cascade to be regular. So this is one thing. We don't expect this problem of duality wall to arise. But on the other hand, we would have to know how to dualize. Okay. So the short story, short answer is that we didn't do the cascade, but in full detail because it's currently unknown how to do it. But there are good arguments that it should work. The ultimate argument would be to find the gravity dual.
Right. I mean, yeah, so part of that's my motivation, I guess, too. But I mean, for my question, the question I have in the back of my mind, I think, is, do you expect the SUSY break-in to be really like at the bottom of the cascade, literally, or to actually be, you know, at every step, you're always breaking SUSY, and in a sense, there is no way to decouple the SUSY breaking from, which is like at the bottom of the throat, to the full setup, which is just SUSY breaking, and then gluing it back to a regular Calabi-Yau, like we were saying at the end, would be much more complicated.
So, okay, so if you purely on the gauge theory side, if you can separate hierarchically the steps of the dualities, then I would say that you see the SUSY breaking only at the last step. Otherwise, you wouldn't even be allowed to do some dualities. If you have a gravity dual a la Klebanov-Strasser, then, as you know, the steps are all dense, no, in some sense. And so it's true that I would expect the SUSY breaking to propagate a bit above, but I don't expect it to propagate, you know, like, I mean, I still expect the scale of SUSY breaking to be the lowest scale. This is my expectation.
Okay.
All right. Do we have more questions for Riccardo? If there are no urgent questions now, I'd say let's thank him again.
Thank you.